So welcome to the second last video, or the second last page in special relativity. In this video we will be looking at the Lorentz transforms. So we know that with the Galilean transform, the object of the transform is to be able to describe the positions in one reference frame relative to the positions in another. And the object of the Lorentz transform is exactly the same, but we need it to work at relativistic speeds. And we saw in the video on special relativity and space-time that Lorentz's contribution to that theory was this transform, so it was the maths. And the way he solved it was he assumed that the transform had the same form as the Galilean transform, but was multiplied by a factor gamma. And that factor gamma reduced down to 1 at low speeds. So using this Lorentz transform, or this form of the transform, we would describe Hardy's position relative to Laurel. So that is Hardy's position as viewed from Laurel's reference frame, as x dash is equal to gamma times x minus ut, where x dash is in Hardy's reference frame and x and t are in Laurel's. And likewise, we can do the reverse, and we would describe Laurel's position as viewed by Hardy, or Laurel's position in terms of Hardy's coordinate system, as x is equal to gamma times x dash plus ut. And the difference in sign comes from the same place the difference in sign in a Newtonian or Galilean transform would come. In the first case, we're considering that the point of view of Laurel, so Laurel's reference frame is the stationary reference frame, and in the second case we're considering that Hardy's reference frame is the stationary reference frame. So these two transforms describe how we transform the space component of space-time. And so the next thing that we need to find is how we transform the time component. So we'll start with our equation for x, for our blue x from Laurel. And the thing that we need to know, the only thing we need to consider, is that one of the postulates of special relativity says that the laws of physics are the same in all reference frames. So that means that the blue x is the same in both equations, and the red x dash is the same in both equations, and so on. So by substituting in our equation for the x dash into our equation for x, rearranging, simplifying, and all the rest of it, we come up with this equation that describes a relationship between the time, t dash in Hardy's reference frame, and the t in Laurel's reference frame. And we can do the same, but beginning with the second equation. And when we do that, we find this equation. And once again, the only difference between the two equations is the plus and minus signs. So now we have the Lorentz transform equations for position in the x direction and time. So I have said throughout this topic that we are working in one dimension. And what that means is I'm looking at the change only in one dimension. But each point in space is still a three-dimensional point. So we still need to know, for our case here, where we have movement only in the x direction, what we would do to transform the y and z positions. And the answer to that is nothing, because neither the y nor the z positions have changed over time. So there's no relative velocity of either the y or the z coordinates. So these are our Lorentz transforms for the system that we're working with, for a relative velocity in the x direction. And at the minute, they're actually not that useful because we don't know what gamma is. So the next step for us is to figure out what the expression for gamma is, and then we can start to use our Lorentz transforms. So in order to figure out what gamma is, we need to use the same, or we need to remember the same thing we did in the last slide, which is that these equations are equivalent because the laws of physics must hold in all reference frames. So we're looking for a way to relate these equations in inertial reference frames, where one frame is moving at a relative velocity to another, and that will allow us to find gamma. So the way that we find gamma is we look at some event that takes place at exactly the same time in both reference frames. So we have here our two-dimensional coordinate axis. So this is not a space-time diagram, this is just our standard coordinate system that allows us to locate some two-dimensional point in space. At time t equals 0, both our reference frames, so x and x dash, are located at exactly the same point in space. And at that time, at x equals 0, and both those reference frames, we emit a flash of light, and that flash of light is emitted in all directions. And now we know we've defined that Hardy's reference frame is moving at some velocity v in the positive x direction relative to Laurel's reference frame. So that means after some time t, both reference frames look like this. The flash of light occurred at the same time and from the same location in both reference frames. So after some time t, the photons in that flash of light have travelled a distance equal to ct, so equal to the speed of light times the time. So we know that the distance those photons have travelled, or the distance from the origin to that ring of light, is equal to ct. And since we're working in a two-dimensional coordinate system at this stage, we know, or we can see, that ct is our resultant vector, and it has its x and y coordinates, which we will call x and y. So by simple Pythagoras, by simple two-dimensional vector resolution, we know that x squared plus y squared is equal to ct squared. And if we make the same analysis on our x dash system, on our system moving with that relative velocity v, we find exactly the same. And once again, because one of the rules of relativity, one of the postulates of relativity, is that the laws of physics must be the same in all inertial reference frames, we know that these two equations are equivalent. And we can use this equivalence to find a value or an expression for gamma. So what we do is we substitute our equations, our Lorentz transforms, for x dash and t dash into that equation, x dash squared plus y dash squared is equal to ct dash squared. And when we do that, we get an equation for x, y, and t in terms of gamma. And we know that that equation must be equivalent to the x squared plus y squared equals ct squared equation. So gamma is the term that makes that equation equivalent. And when we go through the maths, which I won't go through here, we find that gamma is equal to 1 divided by the square root of 1 minus v squared on c squared, where v is the relative velocity of reference frame x dash y dash. And so now we have an expression for gamma. There is one more simplification that we can make to our Lorentz transforms. So we can see that our Lorentz transform for time has factors of gamma squared in it. So our gamma squared is equal to c squared divided by c squared minus v squared. And when we substitute that back in to our equation for t dash, we find that it simplifies right down to t dash is equal to gamma times t minus xv on c squared. And likewise for our other equation from the other reference frame, we get the same. Okay, so now we have our four Lorentz transform equations in their simplest form, assuming that we have only relative motion in the x direction, and we have our gamma. In the next video, we'll look at one last Lorentz transform. We'll look at how we can use it to get the relative velocities of each of our reference frames.